Welcome to Analog Integrated Circuits Design class, and this today is your lecture number 7. And so far in the past two to three classes we were looking at CS amplifier. In yesterday's class we looked at a CS amplifier with a diode connected load, but it was an NMOS load. Now today we will look at diode connected CS amplifier, but with a PMOS load. So yesterday while discussing, we saw that for a diode connected CS amplifier with NMOS load, we saw that there is body effect, and we have even made few observations based on that. So today we will continue this CS amplifier with diode connected PMOS diode connected PMOS load. So I hope you remember the circuit. So this is your input device, this is V in, this is V out, this is M1 device. Now the load device here is a M2 is a PMOS. I have connected PMOS. To make a diode connected, I am just connecting the drain and drain and gate together, and this is connected to VDD. All right. Now, as we have done for the previous circuit, AV can be written as minus GM into R out, and GM is anyway GM1, and R out is R01 parallel to 1 by GM2 parallel to R02. This is R out, right? Now, as we did yesterday, so if we are neglecting the lambda, so if lambda is assumed as 0, then this voltage gain can be written as minus GM1 by GM2. Or if I plug in the formulas for GM1 and GM2, we can write it as GM1 is under root of 2ID mu and Cox W by L1 divided by 2ID mu P Cox W by L of 2. So this is equal to under root of so minus will be kept outside. So GM1 and GM2 you have separate formula. I have just kept in, and 2 ID and Cox will get cancelled. Since your load and input device both are different, you will actually have these terms here. This mu n W by L of 1 divided by mu P W by L of 2, right? Now say for example, if I am okay, so let this be the formula, this be the voltage gain formula, under root of mu n W by L of 1 by mu P W by L of 2. So if I do a comparison with yesterday's expression, yesterday since both were same device, NMOS, both were NMOS, in the expression this mu and Cox term was getting cancelled, but today that is not the case. Moreover, since it was NMOS as the load, body effect was there, and due to body effect you got this eta term. But now body effect is not there, because you know that this is body, and body should be connected to the highest potential in the case of P MOSFET, so there is no body effect, but you are left out with mu n and mu p terms within the voltage gain. Now let us think of a practical case where I need an amplifier where I need a gain of 10 or gain of minus 10. So now the question with me is how to achieve a gain of minus 10. So how can I achieve a gain of minus 10 here? So what we are trying to do here is you have the expression with you. Now to achieve a gain of minus 10, you should know what values of W by L and what values of mu n and mu p you should have. So let's say generally we can say that mu n is approximately twice mu p. The mobility of electrons are considered twice as twice more than the mobility of holes. So if mu n is approximately equal to twice mu p, to achieve a gain of minus 10, what should be the value, or how much should be the value of W by, or what should be the relationship between W by L of 1 and W by L of 2? Can I get some answers in the chat box? You have voltage gain expression with you. In that, considering mu n is equal to 2 mu p, what should be the value, or what should be the relationship between W by L of 1 and W by L of 2 in order to have a voltage gain of value very close to minus 10? Yes. So, in order to have a gain of minus 10, W by L of 1 should be at least equal to 50 times W by L of 2, right? So why, how is this possible? Because if I put this here, mu n is 2 mu p, so mu p and mu p will get cancelled. W by L is 50 times W by L of 1. So if it is under root of 100, that will be equal to 10. That is how you will get a gain of minus. So I have just taken a practical case where you need some gain of 10. But if, when I tried for a gain of 10 for the same circuit, one thing what you can observe is the relationship between W by L of 1 and 2, or yes, as Avinash have written, I would write the relationship between W by L of N and W by N of P. So NMOS and PMOS, or you can see that the size of NMOS should be 50 times larger than size of PMOS. Or here, directly I can comment that there is definitely a disproportion in the size of transistors. There is a disproportion in the size of transistors. What is the meaning of that? So you, in the circuit we have two transistors, and one transistor is yeah, now only I'm remembering. I think the other day I told I'll show the layout of a MOSFET, right? Somebody asked me how with respect to W and L, some question has come yesterday, right? Yesterday or day before. Sorry, I don't have the picture of that. I'll do that shortly. Yeah, so what you can observe here is when we try for a gain of minus 10 for this CS amplifier with the diode connected PMOS load, you can see that the NMOS and PMOS sizes are not in proportion, or uh, if NMOS is have if NMOS is occupying this much area, PMOS size is comparatively smaller, something like this, right? So what I have drawn here as red in rectangles is the area, or the area occupied by both transistors on an IC, and you can see that there is a large disproportion, and generally such disproportions are not really not good in an IC, because there are a lot of things related to this, but I would say here that there is a large disproportion. So one is having a very large size, another one is having a small size, and such disproportions are not generally preferred in an IC, right? Now apart from that, let us check one more thing. So we need a gain of minus 10, but we observed that there is a large disproportion in the size of the transistors. Now let us check about the yeah. So let us check one thing. Let us check the overdrive voltages of the transistors. What is overdrive voltage of transistor? Overdrive voltage is nothing but VGS minus VT. So I'm just checking how this overdrive voltages are related for these two transistors. Now, to check the overdrive voltage, what I do here is there are two transistors here, and both will carry same current, so ID. But ID1 I will mark, and ID2 both are equal. So what I'll do here is, if ID1 is equal to ID2, not if, they are equal, I can equate that half mu n Cox W by L of 1 into VGS1 minus VT the whole square can be equated to half mu P Cox W by L of 2 VGS2 minus VT the whole square. Right. Now, see, I'll tell you why I all of a sudden I have come to check the overdrive voltage. I'll come to that. For the time being, I have just equated the current, and I'm now writing a relation between this VGS2. Let me use a different color. So if I write VGS2 minus VT by VGS1 minus VT, I can write it as so half will get cancelled, C will get cancelled. What you can see is it will be equal to under root of mu n W by L of 1 divided by W by L of 2. Right. So in the previous page, when I have written the gain also is equal to same thing but with a negative sign. But now when you check the ratio of overdrive voltage, that is also exactly the same. So make here is this is same as the gain value. So can I get some response from you guys? Are you guys listening? Are you guys with me? Can I get some yes or no in the chat box? All right. So ratio of overdrive voltages are also equal to the gain value. So what is the meaning of that? So I have assumed a gain value of 10. Now I can write VGS2 minus VT divided by VGS1 minus VT is equal to 10. Right. If I am considering for a gain of 10, the ratio of overdrive voltages will be equal to 10. Right. Now, what is the implication of this when I say that VGS, the ratio of overdrive voltage is equal to 10? Let me assume that, say if your VGS1 minus VT, the overdrive voltage of the transistor M1. So for M1 transistor, say if I assume an overdrive voltage of 200 millivolt, if I assume an overdrive voltage of 200 millivolt, in order to maintain the gain of 10 value, what should be VGS2 minus VT? VGS2 minus VT should be 10 times of this value, which is very close to 2 volts. Right. Is that clear what I have written? Now let me bring the circuit back. So I have the circuit here. I have the circuit here. This is M1, this is M2, and this is ground. I am just considering for a supply voltage of say 3 volt. If I am considering a supply voltage of 3 volt. Now, be very careful. What I am going to do now is something new for you guys. So you can see the circuit diagram what I have written on red on the screen, and the total voltage, the supply voltage is 3. The meaning of that is the total room. If I look for the, so generally we need to amplify signal. So the entire room available is from 0 volt to 3. So you'll be wondering what is this new term, the entire room. So from the supply rails, so you can see the 3 volt and the supply positive, and this is supply positive, and this is ground. We generally call it as supply rails. So that's the minimum voltage in the circuit will be 0, and the maximum voltage of the circuit will be 3. Right. But we know that now I am looking for output voltage available at the this node, at the output voltage, that is at this point. Right. So even though this we are looking at AC, we know that it's a suitable DC voltage. So 3 volt is already given. At the input also there should be sufficient DC. That will definitely establish a output DC voltage, and we know that what is the DC voltage, which is equal to VDD minus VSG. Right. So this DC voltage is equal to VDD minus this voltage here. So if I mark it as VSG, that is the output DC voltage. So whatever it is, if I assume, I'm not going to the details of that right now, but I would assume that this is the DC level, output DC level is this. Right. Now on this 3 volt, the minimum the total voltage available is 3, and you have a DC voltage. Now what we are expecting is you will get actually a output voltage which will swing on this DC, something like this. Is this clear? Whether the statements what I'm making is clear to you guys? Can I get some more response? Can I get some yes or no here? Oh, that means you have, yeah, I'll definitely repeat, Sri Harsha. Okay, so going back, your circuit is CS amplifier with PMOS diode connected. We looked at the gain expression, we got the gain expression. We made one observation that in order to have such gain, the ratio of okay, all right. The ratio of the size of the transistors is very huge, and that is my first observation. Second observation is I checked out for the overdrive voltage, and I saw that overdrive voltage is coming exactly. The ratio of overdrive voltage is exactly equal to the gain value. Now, for a typical overdrive voltage of say 200 milli for input transistor, the load transistor should have 2 volt of overdrive in order to get a voltage gain of 10. So now what I'm trying to understand here is if these are the overdrive voltages 200 milli and 2 volt for both the transistors, how much space will be available in the circuit for the output voltage to swing across, right? So this is your circuit and this is the output node, and VODC is the output DC, and your circuit or your signal output voltage will be swinging like this. But we know that the top transistor, so from this node, if a circuit is swinging, can this voltage go up to 3 volt? My question is, from the output DC, the output voltage when it swings, can it go from this DC voltage to 3? No, it cannot go. If it goes to 3, then your M2 transistor will be off, right? That means you should have sufficient overdrive voltage for this M2 to be turned on and to be in saturation. Similarly, M1 also should have sufficient overdrive voltages for that to be in saturation. That means you will definitely have to leave some space here for the overdrive voltage of the second transistor, and even for here, which is the overdrive voltage of the first transistor. And we for this current example, we saw that this overdrive voltage is equal to 2 volt, this is equal to 0.2 volt, right? Now if I assume a 3 volt supply, from the 3 volt I have to deduct these 2 volt and 0.2, and what I am left out is only 0.8 volt. So I can get a maximum of only 0.8 volt peak to peak when I use the circuit as an amplifier for a 3 volt supply, assuming that the overdrive voltage is only 200 milli. Now, what I am concluding here is, if I go with this circuit, for a gain of 10, I can observe that there is a terrible hit, or the output voltage swing is very, very less, or there is a terrible hit in the output voltage swing. What do you mean by terrible hit in output voltage swing? Because the transistors are consuming a larger voltage to maintain the saturation condition as overdrive voltages, the space or the room available for the output voltage to swing is very less in this case, right? So we call this as, so whatever I am calling this as room is actually the space for the output voltage to swing, and generally we use a term called, okay, I'm not bringing a lot of terms together here. Yeah, so this will definitely cause a hit in the output voltage swing, right? So these are the two observations from this CS amplifier of the diode connected structure, and we have to do something in order to overcome these difficulties, right? So if you have questions, you can ask. I'm just waiting for you guys. If you have doubts, I'll clarify it, or otherwise you can just hold on. I'll just summarize. Yeah, so the point here is I looked at CS amplifier of the diode connected load. Yes, sure, Amitesh, you want me to explain the diagram? Yes, I can draw that diagram again here. Right, now what I'm drawing here is, this is the output voltage, this is the total space for the transistors to be in saturation, and also for the output voltage to swing. So this is considered as the DC level. Now For the upper transistor, there it need. So when I show, actually I should show this much. So this is 0, this is 3 volt, so this is 1.5. So in that 2 means I should show at least this much, right? So this is almost 2 volt, and here I need almost 0.2 volt, right? So this is what I need for the transistors to be in saturation. Now, when your output DC level is this, your voltage, if you want a symmetrical waveform, you can expect only this much, or this much is only the space for the output voltage to move around. That is why I mentioned that there will be a terrible hit in the output voltage swing if I go with this circuit in this way. Or you have to definitely bring in some additional feature into the circuit in order to come out of this problem. Is this clear? So here I made one assumption that your output DC is exactly at the middle, but it is actually not. It may not be exactly at the middle. So the voltages, the values which I have marked, or the scales what I have marked may be different, may not be exactly the same. Yeah, I hope this is clear. Still, if you have doubt, you can please check with me. So what I'll do here is I'll just draw the variance of CS amplifier. So CS amplifier with diode connected loads. This is what we have seen yesterday. So this is M2, this is M1, this is V out, and this is VDD. This is the circuit what we have seen yesterday. Now today we saw the other circuit, which is also okay. That is a PMOS load. So this is VDD, this is M2, this is M1, and this is V out. So both are CS amplifier with the diode connected load. One is an NMOS diode connected, one is a PMOS diode connected. But both amplifiers are using input device as NMOS only, right? So this is input device, this is input device, both are NMOS. So these are, sorry, so these are NMOS input and diode connected load, right? So now my question to you guys is, can you draw the circuit of CS amplifier with PMOS as input and these two variants of load? One should, the input device should be PMOS, and the load devices should be in one it should be NMOS, and other it should be PMOS. Both are diode connected. Can you try that circuit diagram? I think my question is clear. NMOS input and NMOS diode connected is here. Similarly, NMOS input and PMOS diode connected is here. Now my question is to draw PMOS input and NMOS diode connected, and PMOS input and PMOS diode connected. So if any one of you have drawn the circuit, please do let me know. Yeah, Bhuvan, are you there? Bhuvan?
Yes, sir.
Yeah, Bhuvan, did you get the diagrams?
Sort of.
Okay, can you just show me the diagram?
Like, do you want me to send it on the group?
No, you can switch on the video and just show me the diagram.
My webcam is not working.
All right, then you can use send a snap to the WhatsApp.
Yes, sir. Once.
Yes. So those who have drawn the diagrams, can you guys post to the WhatsApp group so that I can just see? So those who have drawn the diagrams, please post in the WhatsApp. I can check it right now. All right. So are you guys posting? Should I wait or? Yes, I think Shri Harsha, you have sent. Shri Harsha, yes, you have sent it. Let me check. Okay, there is a small correction in that. I'll draw the circuit now. And one more is Bhuvan. Yeah, Bhuvan. Okay. Thank you for you guys. Like, thank you since you have posted. So I'll just draw the correct diagram here. So what I was telling is input device should be PMOS, right? So PMOS, as we know that the source of PMOS should be always connected to higher potential. So I will start the diagram only from, see, the PMOS circuits will be exactly complementary to this. So it will start, the input device we should start from supply from VDD. Now this is your input device. This is M1. Now as a load, what you should connect is, you should connect first NMOS diode connected. So this is V out, and this is M2, and this is V in. This is one variant, and another variant is the same PMOS device as input straight from VDD, and then here also it should be PMOS device. So these two should be grounded, and this is V out, and this is M2, right? I hope this is clear for you guys. Now I will write it here as both are PMOS input and both the variants of diode connected. All right. So now, if I ask you guys to find the voltage gain of these circuits, it is straightforward. You can see that voltage gain is equal to minus GM into R. Or what is GM? In all these cases, GM is minus GM1. So it is minus GM1 into what is R out? R out is the impedance seen down in parallel to impedance seen up. So in this case, it is R0 1 parallel to 1 by GM2 parallel R0 2. In this case also it is R0 1 parallel to same thing. Here also it is R0 1 parallel to same thing. Here also it is R0 1 parallel to same thing. So your gain expression remains same, which is R0 1 parallel to 1 by GM2 parallel to R0 2. That is the voltage gain of all these four circuits which are diode connected structures. Right. That is one observation. Now the second observation is, if I specifically look at the output node, see, if you look at this node here, this node, and all these four nodes, one thing what you can comment is all these nodes are low impedance nodes. So you will be wondering now, what is this low impedance node? Output nodes are low impedance node. What is the meaning of low impedance node? If the impedance at that particular node is low, I can call it as a low impedance node. So if I look at this node, I know that all these nodes have low output impedance. What is the meaning of low output impedance? Output impedance is equal to 1 by gm parallel to R naught parallel to R naught, which is smaller than 1 by gm, and that is a small value. That is why we call this output nodes as low impedance nodes, right? Now, one advantage of this is, as I mentioned in the other day, bandwidth is always written as 1 by 2 pi RC. And now, if this R or the output impedance is low, that means the bandwidth of the circuit will be high, or I can use a circuit for even for a larger frequency. That is the meaning of this, right? So another observation is bandwidth is more. All right. So what we have done is we have seen all the 4 variants of CMOS CS amplifier of the diode connector and made 2 observations. One is all 4 circuits have same gain, but the output impedance is low, and since output impedance is low, bandwidth will be more. Right. So with this, I am winding up for today. If you have questions, you can ask now. I'll be happy to answer your questions, because the topics what we have discussed today, you may have some confusion. If it is there, you can ask. Thank you for joining.